edition of the YakRover meeting. And this week, it's a bit of a follow-up of what we've done, I think, 3 weeks ago, where we were talking about simulation software in Unity, which is a game engine, but is trying to do some things in the robotics world. Okay, and there is a lot of appeal activity around it. So we decided to review this at the YakRover project. So 3 weeks ago we did a few things, okay, but it was unfortunately the demo itself didn't work at all. Okay, so here is an occasion to have something that actually works. Okay, and so what we talked about last time is that first, what about simulations? Okay, why we talk about this? Why we want to work on rovers, hardware, and the software in it. Okay, and so the point is that having simulations is actually very useful when we develop, test, and debug, especially the software, but also the hardware when we are designing, for example, rovers and more generally robots, basically. Okay, and so this thinking has spread across the industry, and we can see that in the robot operating system, also ROS, this ecosystem, there is for ages there is a simulator called Gazebo, okay, that helps doing just that, develop, test, and debug robots. And now it's even backed by very large companies, including Amazon, Google, and others. Okay, so simulation is extensively used, for example, on AWS, so the Amazon cloud platform, with an offering called AWS RoboMaker, okay, that allows to test in Gazebo and some other simulators and to run everything on the cloud. Okay. You have also NVIDIA, okay, that is quite active with their Isaac simulator. You have Unity that we'll be talking about today with the Robotic Hub. And there are actually more and more startups working on simulation for robotics, especially on visualizations. Okay? We can have a look at that, but there are more and more visualization startups for robotics, including self-driving cars and so on. So today we continue with the Unity for now. Okay. And last time we had a review of the Unity tools. Okay, we will review that again today. We'll use them more extensively. And last time they had a bunch of tutorials. Okay, and so the practical part of this talk is about talking about these tutorials. Okay? And last time it was a robotic arm tutorial where there were pose estimations. That is, the arm automatically moves one object from one place to the other to some target. Okay, and so this tutorial is a bit old. It's a couple years old. Okay, and despite quite nice documentation, honestly, and quite nice guidance, I couldn't make it work. Okay, so I tried again this time. And after a couple of hours, I really stopped and moved to another one that we will be talking about today. Okay. So before showing the simulation, just about what the simulation will do. Okay. And dig a little bit more about the sim for rob, so simulation for robotics concept. Okay. So when we are building a rover or robot, okay, we have three aspects. Okay, so from the right we have an environment in which the rover will live. Okay, so for us at the YakRover we're interested in space, but here we'll talk about something simpler, more common, more reachable. Okay, which is, for example, a warehouse. Okay, and inside this environment we put some hardware. So here the hardware is a small rover called the Turtlebot 3. Okay, that is an open source, open hardware and open software rover. Okay? And on that hardware, we've got a bunch of software to do something. Okay? So, for example, inside the warehouse is to pick packages and move them from place to the other. Yes. Oh. Okay, so that's in general when we develop a robot or rover. Okay, these are the three aspects that we are looking at. Okay, and so there is a typical loop. Okay, where we start by writing some code. Okay, and software developers do what is called testing. Sometimes they do something called verification, and sometimes they also do something called continuous integration. Okay, to check their software at a rather low level. Okay. And once all the tests are good, they test their software on the robots in the target environment. Okay? And usually we find some issues, and so we are back to write some code and we loop for some time until we are happy enough and we deploy. Okay? And so the problem with that is that to test on robots is very expensive because we have to typically the software is compiled for the robot, is sent to the robot. After there is sometimes some calibration that happens with the new software and so on. All that takes a lot of time. And after we have to run some test scenarios, okay, which on a real robot will take real time, which can be very long. So, for example, to move one packet from place A to B, if it takes 10 minutes, it will take 10 minutes. It's uncompressible. So it's very expensive in terms of time, in terms of pace, okay? Because when we are doing software development, we've learned from the ages that a CI, so continuous integration, to have a tight, closed loop, can be very helpful, okay, to test IDs and so on, okay. And so on a real robot, on a real hardware, we lose all that, okay, because just the final test takes ages, okay. And so this is where we add a box here. So it's actually the same loop, okay, where we have to write some code, testing, CI, and so on, and test on robots. But we have an intermediary, which is to test on a simulated robot and a simulated target environment. Okay? And so in simulation, if all is good, we move to the real hardware. Okay? But if it's not good, we know it actually pretty early because everything is software, and we can get back to write some code. Okay? So the point of introducing simulation is that we have a cheap iteration loop. Okay, it can be cheap in terms of time; it's faster. Okay, and it can give some degree of feedback while we are writing the software. Okay. And what is interesting is that the software is running on a simulation, but it's exactly the same software that is going to run on the target hardware. Okay? So we have this small loop that becomes faster, so we can rather quickly and automatically check a lot of things. Okay? And when we're happy, we can move to the more expensive loop to do the final checks, okay, before deploying. Okay, so simulation for robotics. So one important point is that we are writing the software only once, okay? That it runs on virtual and after on real environments and robots, okay? Just to speed up everything. So it's usually we get a faster and cheaper development loops, okay, which has many advantages in terms of psychological pace, okay, and also the cost. Okay, we get things faster, okay, at a cheaper cost. A big advantage also that is interesting for the YakRover project in particular, that we can test in environments that can be really extreme conditions that we don't have direct access, typically space. Also, a couple of years ago, we had a talk from the OpenRover founder, okay, where the rover is going into water, okay, and rather deep. Okay, so we can test all that in a simulator without lifting a finger, basically. Okay? So on the downside, there is a problem called the sim to real. So it's a simulation to reality. The sim to real gap. Okay, it's typically that simulator. There is a limited amount of fidelity compared to the real environments. Okay, some simulators they don't have a physics engine, for example. Okay, to simulate gravity, stuff like that. Okay, and so even with very good simulator, there is always a gap with the real robot. So that doesn't. If everything is fine in the simulated environment, doesn't mean that it will work perfectly on the real environment. So there is still the need to test on the real robot in the end. Okay. The point here is that we can catch more problems faster thanks to using a simulated environment. And you will see also that even today it's still complex to set up this environment with simulator, and it's costly to it can be costly to build a simulated environment. Okay, so less costly than building the real one. Okay, but still a significant amount of time, especially for software developers. Basically, we need people dedicated to build the environment. Okay, you will see that in a moment. Okay. So back to the scenario, and today it will be about the Unity simulator and the ROS2 software stack, okay, to develop robots. Okay. And the scenario is a navigation scenario. So it's about this rover going through a warehouse from point A to B, okay, using a family of algorithm called a SLAM, so for localization and mapping. We won't enter the detail, but there will be references on the algorithm used in this demo. Okay? And so we have these three aspects: software, hardware, and environment. And so here that becomes the environment will be a virtual environment in the Unity simulator. The hardware will be a virtual hardware, so a 3D representation of the robot. And the software will be the ROS stack and something called Nav2, which is a navigation package that is using SLAM in the ROS ecosystem. Okay, so before showing the demo, okay, everything runs on a single machine here. Okay, so we have the Unity simulator that will simulate the environment and the hardware. Okay, and we have the software. So some people call that the brain, okay, of the robot. Okay, that will run in a container on the same laptop. Okay, so it's a container is like a simulated computer. Okay, so where we run the ROS software, the navigation software, the control, it's implemented using behavior trees that we talk about sometimes, and some other facilities. Okay, and so the facility is sorry, and that is connected through something called the ROS TCP connector. Okay, so basically the brain is communicating to the body hardware, okay, through this connector. Okay, and finally there is this NoVNC thing, okay, which is basically a web server, okay, so that we can have a UI to the brain in a way, okay, that we can see in the browser, okay, so that we can actually send commands to the rover to go from A to B. Okay, so this slide just shows that everything runs on a single computer. Okay, so everything is simulated, everything is running as software on a single computer. Okay, since we are using something called DCP, okay, which is Internet technology, they can run on several computers, but it's just to show that we have the complete software, hardware, and environment running inside a single computer if we want.
Eric, just one question. Where's that computer?
It's the one I'm presenting with.
Okay.
Okay. So it's a plain laptop, okay, and not a new one. I mean, I think my laptop is from I bought it in January 2020, so it's at least 3 years old. Yeah, I mean the technology is at least 3 years old. Okay, so I found this out because you will see that it's running pretty well. Okay, despite having a laptop that is not the latest technology, let's say. Okay. So if we move to the demo, if I switch screen, I hope you can see. Okay, do you see this black window?
With the desks. I mean, with the bookcases with boxes.
Yes. Okay, so this is the main window from Unity. Okay. And so just a quick review. So most of the demo will happen inside this. Okay, so you can see the simulated environment. Okay, so here, sorry. So I hope you can see if I don't go too fast. Okay, so it's a simulated warehouse. Okay, that we can see here. So it has some shelves, okay, some boxes and so on. And so it's 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 a real 3D environment, okay, in the Unity tools, okay, which is for games, okay. So it's like a game basically, okay, in which we can evolve, okay. And what is interesting is that we have this environment, okay, where this our target environment here, okay, and we have the rover here that you can see just on the floor, okay. And the thing that is pretty cool, okay, is that it's not like we have one environment, okay. We have actually for a given scenario, we have an infinite number, okay, that we can generate, regenerate, okay. I hope I'm not going too fast, but maybe you can see that the position of the shelves, the number of boxes on the shelves, where the boxes are, the angle of the shelves related to one another that are different. Okay? We can randomly generate many scenarios, okay, and we can have way more shelves, for example, okay, or way fewer, like that, and it's just to test the different scenarios, and all that is code basically. Okay, so we can automate. For example, we can automate 3 categories to have an empty warehouse to a bit busy warehouse to a very busy warehouse. Automatically generate that as environment where we like to test our rover. Okay. You can also see, different lighting. Okay, so we can control the light. So it's a bit more involved to change. To me, it's a bit more involved to change where the light comes from. Okay, but the thing that you can see that if I get out of the warehouse, you have a really complete building basically. Okay, and we can. So there are several things we have under control. Okay. And so if we go back to something a bit more interesting, okay. Okay, so this is typically what we have. Okay? And so, interestingly, I've lost my rover. Where is my rover? It's under the shelf, interestingly. Okay, here we go. Okay, so that's about the environment. As for the rover, okay, it's you can see it here. Okay. So this is something that Unity has done pretty early. Is that how can we create a virtual version of a real hardware? Okay, because most of the hardware, they have a CAD file. Okay. And it turns out that the Turtleboat 3 that we're using here, this small rover, has a CAD file that is created with the Onshape. Okay, so I talk about Onshape because we had a talk presenting Onshape maybe a year ago, something like that. Okay, which is a bit like Autodesk and so on, but a bit more flexible and more accessible to me. Okay, and so the model is available there. You have a link in the presentation. And what Unity does is to create a software module called URDF importer. Okay, so URDF is a common file format in robotics for for the hardware design. Okay, which means that if you have such a common URDF file, which is common in the robotics world, okay, you can just import it directly here. Okay? And so this is what happens here. So I don't review that, but I don't demo that. But the result is that we get a robot that is defined in a common format in the robotics world. Okay. And so now, in the presentation, I said we had the virtual environment. Okay, this is what you see here. The virtual hardware, you see it here. And after we have the software. And the software runs in a Docker container. Okay, so I'm going to start it. So it should run just like that. Not just like that, sorry. We should be good this way. Okay. So basically here I'm starting the brain, okay, of the rover. And so if we how does it work? Okay, yes. There is a last component that we need, okay, is basically to be able to talk to the brain and to tell it what to do, okay? And for that, the way it's done here is that we get a small website that is created. So that's how it's done in the tutorial, okay? It's there are many other ways we can use. We can use a keyboard directly, okay? We can also use for example, a game controller. Okay, there are some in the ROS ecosystem. We can use a game controller, so we could directly control the rover. Okay, so sorry, I will pass a bit on the technical detail here. Everything is explained. The only thing that I need to now basically start the brain. Okay. Okay, so it's Unity. I think it's a SLAM. Sorry, I don't remember the name. Unity SLAM. Sorry about that. Some example. Okay, sorry. Okay. So sorry, the command doesn't matter really so much. Okay, it's a standard kind of command in the ROS ecosystem to start the software. Okay. And so here is a technicality, something I haven't managed to solve automatically. Sorry about that. Okay, take just a few seconds. Okay. So it starts the brain, okay, behind it, okay, and this tool, I will talk about it later. This tool is how we give commands to the rover, okay. So I will show you that right away. If I manage to, okay, sorry. Okay, so here we just okay, sorry, 1 second. So I studied the brain, and now I need to connect the brain to the environment. Okay, here we go. And now if we will start seeing, yes. So you see now in the environment, there are these red dots, okay, these white dots. I will talk about that in a moment, okay. Just first, I like the rover to be at the base of this green arrow in this direction, okay. And you see now that the rover is moving, okay, showing a lot of things that I'm going to explain, okay. So it's moving as expected, and in the control center, we also have some data. So this is how it's structured for now. Okay, there is duplication, but this is how it has been working for this tutorial. Okay, so here I'm giving another, and so we can see that the rover is evolving according to the command. Okay. So one more, just let's go somewhere here. Okay, so while it's running this route, which could be a little bit longer, okay, just let me explain a little bit more what you can see. Okay, so the pink kind of tube you can see is represents the plan of the rover. Okay, so now it's a navigation stack. Okay, so it's going from A to B, but the way this kind of software works is that it will plan. Okay, what's it going to do? Okay, and so here we represent, in advance what the robot thinks in a way. Okay, is going to do. It's updated in real time. Okay, so if suddenly you put some object, this pink part will turn around the object and so on. Okay, yeah. That explains the pink one. Okay, the white one is the map that the robot sees. Okay, so as you can see, it's centered on the robot and it updates based on where it is, because there is a lidar. Okay, so a laser. Okay, that just turns and collects points. And so what is pretty cool is that we can show all that basically. Okay, so this is about the map, so I can remove the map, okay, so that we can still see everything. Okay, but maybe in a more let's say that the map thing, we know it's working properly. Okay, and so we don't want to see it anymore. So we can just remove it. Like we can remove this this plan. Okay, so we can just hide it, okay? Like that. Okay.
I have a question, Eric, regarding the
Yes.
word map. What you're showing us is data in the reference frame of the simulation. If the rover is actually building a SLAM map, can we show it in a separate window? A view into the rover's brain?
So I think so. Okay. It's just I don't know yet how to do that. Okay? I remember seeing a demo where there is a camera mounted on the rover. Okay, and we can have that camera view. Okay, so in this tutorial code, okay, there is no in this scenario anyway, there is no camera mounted on the rover. So I guess that's why we can't have a feed from there. Okay. I wonder whether we can have a virtual camera that we put on it. Okay. I guess possible, but just not covered here. Okay, so you remember when we made a presentation with in your garden with the spider boats? Okay, we had a video feed directly from from what the boat was seeing inside your garden. Okay, and when we did also the competition with the two spider boats, there was this video feed. Okay, so but we had the video feed because there was a physical camera on the spider boat. Okay, in this scenario there is not such a camera. Okay, so that's why we don't have it. So if we do, then I think we can have a map like that. Yes, because
But that
when we have
map,
basically here. So sorry, just to finish that in this list we can see all what is called the ROS topics. Okay, so in a ROS software stack, okay, there are several software nodes, okay, that interact, okay, to do whatever they need to do. Okay, and they need some input, but they also publish some information. It's called a topic. Okay, so all of them are accessible here. Okay, sorry, and we can show them or not. Okay, and so I showed earlier the map. Okay, the map is what is built from the lidar sensor. Okay, I showed also some the plan. Okay, but there is also what is called the scan. We don't see the scan here. Okay, and other things like that. So we can represent quite a few things. Sorry, you wanted to say something else?
no, I think you answered basically that it's possible to get data from the simulation of the rover itself, of the internals of the rover, and puts them on a side window so we can see what's happening inside the rover.
Yeah.
I think you said that. Yeah. Okay.
So here, yes. Okay. So basically, what is nice in this integration between ROS and Unity is that we can access quite meaningful information. Okay. So here, I can show you something else that is quite interesting. Is maybe you can see these red dots. Okay, red. But if you look at the close red dots, close to the rover, they are red. Farther away, they are yellow, and even farther away, they are green. Okay, if you can see. And so if I make the rover move, maybe you will see its update as well. I lost where it is. I may have just stuck it. Okay, to some extent, it doesn't respond to command anymore. Okay, which I guess happens with real-time demos. Okay, but this is a laser scan. Okay, and we can have different representations. Okay, so here the angle. Okay, so unfortunately it doesn't move. I will try to restart. Okay, but here is the angle because you know the lidar a laser scan basically scans and so moves. Okay, the laser is typically these are the rotating scanners. Okay, and so there is an angle. Okay, and so as we move around, this color scheme is pretty interesting. I'm not so sure how to interpret it. So I much prefer the one with distance, that what is close is red and what is farther away is green, basically. Okay. And we can play with that basically on the showing big dots because we want it to be very visible. So you see here it's gradually from red to orange and yellow and green. Okay. And we can have very fine, even finer. Okay. If it's a problem in the view, I will try to restart the connection. Is there any question? If or maybe I went a bit too fast or something like that.
Are you able to hear me?
Sorry.
Sorry, are you able to hear me? Maybe.
Yes.
Yeah.
Yes.
Yeah. Okay. I was just going to ask. We spent a lot of time in the Unity kind of interface, but I'm also curious about what the other interface that's running on Rover. That is like, I'll try to understand what exactly we're seeing here, because it seems like it's more detailed than just what a laser would put out or something. Or I don't know. What's it estimating in this other screen?
Yes. So, first, it's a bit messy to demo that because there are three windows. Okay. So this is why I wanted to in the presentation to an attempt to give a map of what's happening. Okay. The three screens are basically the three we can see here. Okay. And so there is a container container. Okay, that we see here. Okay. There is the Unity screen, the big one, and what we have in the browser, okay, that is served here to give commands, okay. And what is important is that basically the environment and the hardware, so the body, they run in Unity, okay. And after the software runs in the container, and this software is exactly the software that would run on the hardware. Okay, but instead of the hardware, it runs here in the container. Okay, and there is this connector that makes it communicate with the hardware. Okay, so it's like taking the gray matter out of the hardware. Okay, putting it in the container and putting a link between the two. Okay, so transhumanist, you will be very happy to see that basically. Okay, and so what is important is that basically the software that is demoed here is exactly the same software that will run on the real TurtleBot 3. Okay? There is no more or less. Okay. Well, no, there is more because in the container there is this RVs tool. Okay, it's the one that allows that's this one. Okay, this is the RVs interface. Okay, and there is this small server that allows to see to see RVs, okay? But these three ones, ROS2 7 nodes, nav to slam and the behavior trees are exactly the software that would run on the robots. So did I answer the question completely, or missing the point?
No, that's a great start. So the other screen is RViz, is the application that we're seeing, and that's reading the same ROS topics that Unity is reading to generate this visualization. Is that right?
Yes, yes. So it's a bit messy, but this is how the tutorial was structured. Okay, so here, basically in the tutorial, RViz is a visualization tool that is part of the ROS ecosystem. Okay, so in this tutorial, they start by using RViz to show, okay, so you see it's working basically. Okay, but the thing that RViz is an open source tool that is not as capable as the Unity engine. Okay, so after that they connect. Okay, so first we start with the container and RViz. Okay, and after we use Unity to show the advantage. Okay, the difference. So the here I think it's pretty useful, pretty apt to use RViz. Okay, but when we look at Unity, we have a realistic environment and we can generate environment and so on. Okay, so it's to show this because of this tutorial structure. This is why we end up with this redundancy between the two. But as you said, in RViz we are seeing the same sensor data, the same topic, ROS topic data than we see inside Unity.
Well, it seems like so. I guess my mental model of this is that Unity is essentially reality. And then you happen to be able to also overlay the things that the rover has determined about reality on top of actual reality, which is Unity. Whereas RViz has no concept of what is actually happening. It only knows about what ROS says.
Yes.
Okay.
Yes. You're totally correct in my understanding. Okay, is that you see when you start RViz, there is nothing. Okay. It's once we start receiving the sensor data that we start seeing these blackish structures and so on. Okay, because this is basically the map that the rover is constructing from its sensor data, okay, and publishes on its topic, and is shown here basically.
So here we use RViz to look into the mind of the rover and see what it sees of the world.
In this case, yes. Okay. Yeah. I think in general we don't even need RViz, okay, because we can work directly in Unity in these settings basically.
Right.
So cool. I say we don't need RViz, but RViz is more concise, much more focused. Okay, so I would say that as an intermediary tool, it's still very useful. Sorry, it's suddenly super silent. Did I lose connection or?
No, that covered my question.
Okay.
Very cool. I feel like maybe my video isn't working. I don't see myself updating in the feed.
I see you moving just fine.
Oh, okay.
So I'm trying to restart because apparently the commands do not go through the bridge anymore. Okay. But welcoming, we have 50 minutes more, so welcoming more questions at this point, if any. Otherwise, a few more slides to.
How much work is it to set up a simulation like this?
So it depends a bit what you mean by the simulation like this, because okay, I would say that there are two main categories. Okay, this is when we are in a standard scenario or when we are not. Okay, and so what is a standard scenario? Typically today it's it's about warehouses, a bit of some agriculture situations, what do we have? We have typical arm robots, okay, say tabletop arm robots to do something like moving objects, okay. So if we are in one of these typical industrial scenario, usually the base environments, okay, so generated environments exist, okay, so we can reuse them, and so then obviously it's kind of much less work, okay. So as we've seen, we'll try to restore that, okay. As we've seen, we can generate the environment and we can even randomize the environment, okay. And so it's pretty powerful. It's yeah. So that's one category. And after there is the category where we have, you know, like for example for space, okay, there is some content that is available, but much less to my understanding right now. And then is more work because we may have to create 3D models. We may have to make procedural models. So, for example, to create terrains. Okay. So, for example, 1 year and a half ago, when Fabien came to present his work for a NASA challenge about generating moon environments. Okay. That took him and his partner on the project. That took them, both of them, 6 months basically to get something. Okay. So and it was just, you know, a piece of somewhat flat land on the moon basically. So there was no they simplified. There was no crater or stuff like that. Okay. And so just to wrap up on this, on my answer for now, is that for me, there is one difficulty with creating such kind of environment, is that it's not only about software, okay? It's because the goal is to test software, okay? So it would be nice if it could be just the standard skill set of a software engineer. But here we want to create 3D objects. So it's more the skills of a game developer or a world builder, so such kind of stuff, okay? So skills that are pretty outside of the standard skill set of a software developer. And that can be pretty tough because for me, when I'm in front of Autodesk or Onshape, okay, basically I have to switch brain basically to be able to do anything in a finite amount of time basically. Do I cover everything you wanted, Meyer, or is there something else?
Well, I wanted you to say it will take 2 days. Okay.
But
You cover.
It depends because you see, if I'm working on a warehouse project, well, I think in the setup. Now I understand what is available and how it works. The setup is done basically in half a day, basically. Okay, to create a new project and to pack everything nicely inside a GitHub repository, so that it can be reusable by others in the team. Yeah, in half a day, maybe 1 day, it's done. Okay. But if I'm doing something that is where there is no 3D assets ready, then for me it would take weeks. Okay. Sorry. So, Red, where you see when we start RVs, we have basically nothing. Okay, it's an empty environment. Okay, so we can see the first the initialization of the sensors here. Okay, but this is when we start moving, basically, that everything gets updated. Okay, we started moving. Okay, so this is where the data starts to stream and gets updated. Okay. So, and we can see the readings from the scanner also evolving. Okay, so from red to orange and yellow and so on. Okay. So, Mayor, so sorry I couldn't answer 2 days, but it's either it's 1 day or it's weeks, depending on whether we the 3D assets are available or not.
Yeah, but the 3D assets are not part of the problem. And the question is, how long does it take to set up a robot? We assume that the assets are provided by somebody else. We have a standard, asset.
Okay. And so what do you mean by set up the robot?
I have a robot with 6 legs. You have a robot with 3 wheels. I don't know.
And so assuming we have the 3D assets, okay, so then the next question is what is the software stack? Okay, so in the case of Unity, they are betting on ROS. Okay, so what they've created is not a handful of plugins, okay, to facilitate working with a ROS-based rover. Okay, so if you're ROS, it works. If you're not ROS, it's I'm not saying it doesn't work, okay, because there is no, I don't see any reason it would not, okay, but it will be more work, for sure. So just, I had a few slides about that, okay, about a bit what's happening. So, yes, so on here you can see a bit what, that's from them, okay, that we have the ROS network. The ROS network is basically the brain, okay, so what is running the container. So we have the ROS2 server and the NAF2 SLAM algorithms set and so on. Okay, and so this is what we develop usually. The right hand side is what we develop when we're developing with ROS on the rover. Okay, and here the arrows, the lines that go to the other box, I will come to that later, are the ROS messages, so the topics. Okay, and so these are the plugs basically of the brain. Okay, and so usually we plug that directly into the hardware, so to the real sensors and the real actuators and so on. Okay, but what we do here that we unplug all that and we plug that into Unity through their integration software. Okay, so that we can see on the left hand side. Okay, which are the ROS service script, ROS subscriber script, and ROS publisher scripts. Okay. And so you see, everything is ROS something basically. Okay? So in, I think in the code is open source, so it could be adapted to non-ROS. Okay, but that's not out of the box. Okay, so we have to some code to write. Okay, so if the rover has 6 legs or 3 legs or 3 wheels and so on, okay, matters less, assuming we have the 3D assets. But after it's the software stack. If it's ROS, it's supported, especially ROS 2. I haven't tried ROS 1. Okay. If it's not ROS, there is definitely more work. Okay. It's I haven't reviewed the code for that, but there's definitely more work here. Okay.
So just to make sure that I'm understanding how these pieces connect together. So like assuming everything's ROS, there is a script that runs in the Unity environment that does things like emulate an IMU. So it will look at the Unity environment, see what's going on in there, and it will end up publishing data over some ROS. So I guess it's a publisher script. It would like view the environment that's running in 3D using Unity, whatever APIs, and then translate that into a data stream that comes over ROS.
Yes, yes. So yes, in general, after I don't have the particulars, what I know is that inside Unity, they have a physics engine. Okay? Mm-hmm. So there is feedback from that, okay? That is published. And so...
Yeah. So that would be the other part of like, if you're setting something up custom, depending on whether the sensors and the data streams like exist already in the Unity ecosystem, or whether you have to write your own, that's a pretty big gap in like what the amount of work you'd have to do to set up a proper simulation. And it's all work that you would be doing on the simulation environment, not work that you're doing that translates to anything else.
Yes, so that sounds daunting, okay? But the good news is that this code, okay, this ROS code is open source. Mm-hmm. So we can at least understand what is done. And there is another thing that even if we don't have a ROS-based rover, maybe it's easier actually to build in our own code a ROS communication adapter, basically. Okay, that inside the rover, okay, we have our code, I don't know, written with another framework, let's say YARG, okay, and to have another piece of code we write, okay, which would be maybe a ROS adapter, so that all the communication with Unity goes through the ROS adapter. So it's still more work, okay, but it's maybe something that could be easier because ROS is more standard, okay.
Yeah, it could be helpful to be able to mix and match some of the ROS tooling as well. Like you could still use ROS Viz to see what the streams are saying, and then your own code could do whatever.
Yes, indeed.
But it could also be interesting to see what those scripts that live in Unity look like just how hard is it to write a fake sensor that like looks at the 3D scene and then decides what the answer is.
The code is not so significant. If I just had a quick look, okay, so here you see it's I think there are links on the talk, but in the slides, okay, but here the ROS TCP connector is what connects ROS to Unity, okay, so it's a TCP bridge, okay? And it's open source, okay, so I haven't checked to what extent it's open source, okay, but the amount of code is not super significant, okay? So I think it's C++ or C#, is it? C#, yes, of course, C#. Yeah, because Unity for forever, okay, so when I was using Unity, it was 2014. It was already, everything was C# basically, okay.
Are the Unity, like, is there a repo that has like the ROS like sensor? Well, I don't know. Is the sensor a script, or is it, I think it's part of this TCP connector part?
I'm not completely sure, because the thing is that if we look at
this might just be the thing that knows how to speak ROS, is what you're saying.
yes, and so to speak ROS is basically to follow the topics formats, okay, which are basically streams of text messages that are formatted in a certain way, okay. And
so there might be a piece in there that's like, I see this, like the sensor messages, you've got one for like battery state. So there must be some like simulation in there that just knows how to generate battery state messages.
And so here, if you see on the right hand side, so sorry, it may be tiny, but this battery state you can see here is basically an what they call, I think, a game object. Okay, it's something that has a reality inside the virtual environment. Okay, and you can configure it on the right hand side, and you see here there is an attached script. Okay, which is the battery state default visualizer. And so I think we can. There is one way to open the actual script to see it. Okay. And so basically, it's how's it work? And so basically, the script, you know, is a bridge between the source and the. Yeah, it looks like a typical. Okay, but here's the script. So sorry, I don't support C#, so it's going to be pretty hard to read.
Yeah, no, that makes sense. So this script looks like it's how you take those messages and then display them inside of the Unity UI. Yeah.
So you see, we take in the message cell voltage. Okay, so it's a battery state message object, so defined somewhere. Okay? And I guess this is the kind of work we have to do with that, is to map the ROS topic. Basically, is a specific format. Okay, it's a stream of messaging of a specific format. Okay, and so I guess this battery state message we can see here is a map of this structure to a C# object. Okay, that defines a cell voltage. Okay, so we get that voltage, and after we pass it to a GUI object that will show the voltage, basically. Okay, so we can imagine that on the rover there is, one of those kind of battery level display. Okay, and so the game object would be this display, and that would update that value based on the content of the ROS topic message. So it looks like, this this repository called the ROS TCP connector is aptly named. Okay, it's just a connector, basically mapping a bridge, mapping one format to the other, basically. And so here is to map the ROS topic text format to the C# object format adopted by the Unity virtual environment.
Very interesting.
Overall, it's pretty cool. Okay, I see how it can be used, but we mentioned last week. I mentioned my feeling that it was really, it's a patchwork skill for Unity. Okay, they call that the Unity Robotic Hub. But when you go to GitHub and so on, look, the code hasn't moved for a year for the TCP connector. Okay, so we would think that it's a central piece, but if we look at nothing has changed. Last commit was February 2022. Okay, so and there are only 150 commits. Okay? And
it was that good. It was that good.
It's done.
Yeah.
Yes. Well, the thing that, for example, there is a repository on the UADF importer. Okay, so UADF is the format to specify robots and so on, pretty common. So this repository, I'm not so surprised that maybe it's not evolving so much, because the format is kind of settled, okay, for many years already, and doesn't seem to evolve so much. Okay, so yes, sure, but you see during the demo, the bridge collapsed once. Okay, to be honest, while I was learning all that and so on, it never collapsed. It was they say in the documentation everywhere, oh, it may collapse and so on, be careful. So then just restart whatever, and that's what I did here. But honestly, I spent already several hours with this stack, and it was working fine. Okay, but when looking at GitHub, everything open source. Okay, the code, the tutorials, the videos, and all that, all of them are at least a year and a half old. Okay, so at least a year old. Okay, without
even the Unity Robotics Hub hasn't been updated.
Yes, February. That's for me the most surprising one is that
wow.
This one, sorry, this one is which they present as the homepage where you have everything. Okay, last commit was also interestingly exactly the same day as the RCP, the ROS TCP connector, same day. Okay, so. Well, it's a big company, so and also there is competition from, especially NVIDIA now pushing a lot with ISAC and whatever they want to do with this Omniverse kind of stuff. Okay, so they must have a strategy, a big company strategy, where everything is closed source, and after there are drops of stuff that goes to open source. Okay, so. They may just update every once a year or something like that. So maybe we should wait until February 3rd this year to see an update. Okay. But the impression, okay, is that yeah, there is potential and so on, but it doesn't look like they're really investing into it. Okay. And so for me, I'm co-building a small company here where we see a lot of potential in simulation for robotics. Okay. And right now it's really gazebo. Okay, everything is on gazebo, but we have some prototypes that work also with Unity. Okay, and when I say working, meaning for us everything is in the cloud, everything is automated. Okay, that's what we want to bring. Okay, but Unity is a pain. Okay, it's really a pain to use, especially because of their licensing system, but also because we're not sure where that goes, basically. Okay, that it's not evolving, and you see there are some people sending pull requests. Okay, and so I didn't look at these ones, but you see it's January 2022, March, July. Okay, and they are not closed. Look at this guy made something quite comprehensive, and no one looked at it. Okay, just their bot to say, okay, the CLA is okay, and that's it. Okay.
Eric, I have to leave.
Yep. Oh wow.
I don't know if it will. I don't know if it will interrupt your discussion, and I don't know if it will interfere with the recording.
I better drop off also.
No. Let me drop off first. I'm really interested in finding out what happened.
Oh, okay.
Yes. So let's find that out. But anyway, otherwise the presentation is basically over. Okay. So anyway, because sorry, I haven't seen the time. Okay, but anyway, we should stop here. Okay. So thank you everyone for joining. And if you have questions, anyway, I keep on working a little bit on that. Are we still online?
I think we're online. How would we know if it's recording? Oh yeah, there's a little recording symbol.
Oh yes, it's recording.
Oh wait.
Okay, because we couldn't start the call without Meyer, so that was
interesting. Yeah.
At least we can end it without him. Okay,
yep.
But yeah.
Good to know. Well, thanks for that. That was great.
Yeah, thank you for joining, and we'll see you next week.
All right. Later.
Cheers.